All right, I guess we'll get our next talk of the session started. So it's my pleasure to introduce Professor Collin Broholm from Johns Hopkins University. Professor Broholm really is one of the world's leaders in understanding spin structures and how to measure them. And so it's also really well renowned for being a very careful experimentalist. So it's again, our pleasure to host him here. He did his PhD at the University of Copenhagen, and then moved on to a stint as a postdoctoral researcher at AT&T Bell Labs, where then eventually after that he moved to Johns Hopkins University, where he's now currently a professor doing really wonderful work. Today he'll be giving two talks, one today, one tomorrow. His first talk is titled Classical and Quantum Spin Fluctuations in Frustrated Magnets. Please join me in welcoming Professor Broholm. And yeah, the floor is yours.
Great, thank you for the wonderful introduction. Is the microphone functioning?
I think so, probably. Yeah.
Yes. Good. All right, cool. All right, so this is actually a bit of a change of pace because you've been doing a lot of 2D materials, and I think not entirely, but mostly. And so I'm here in part to show you that there's a lot of interesting stuff too that can be done working with materials in the bulk solid form. This means actually a lot of interactions between physicists and solid-state chemists, which is really enjoyable and magical, actually. Sometimes something really exciting comes out of this interface. There are also a lot of experimental techniques that we have in this field, and there's a lot of ability to make direct comparisons between kind of high-level theoretical work and experiments. And I noticed that there are a lot of theorists in the audience, so that's great. We're able to measure things that are very closely connected to the theoretical framework that we use in quantum energy body theory. And so in this talk, I'm trying to give a little bit of an overview for sure. And I have three kind of main components that we're going to work with: triangular lattice and pyrochord lattice. And so the two first parts have to do with the triangular lattice. And then we turn to the pyrochord lattice, where I have a couple of systems we're going to talk about. And so these lattices are chosen because they frustrate the dominant interactions in the system. So if you just think about the dominant interaction, then you will actually have some degree of a degenerate ground state, or maybe we should say that there are many states that actually can satisfy those nearest neighbor interactions as well as you can. But actually, there will always be some dissatisfied interactions, if you want to state it like that. And so then what we'll really be talking about how this degeneracy gets resolved by quantum or thermal fluctuations. And then what kind of new phase of matter can result from really lifting the degeneracy of this manifold that we start off with. So that's the rough picture. And in both cases, I'm going to start off with Ising models, which are fairly simple to formulate and can also be realized experimentally. And then I'm going to add in quantum fluctuations, which is easier said than done in terms of the materials, but it can actually be done. And I'm going to show you how that happens. And then I'm going to show you how we use neutrons sort of as the main probe to look at these things, both in terms of their static structure and their excitations. And so during the talk, I wasn't quite sure how to kind of position the talk, but I think it's useful to have a little bit of a tutorial style to it and a little bit of latest research results. And so I'm going to talk about some fairly recent research results, but I'm going to throw in little nuggets about how we actually do some of these things, both experimentally and how we interact with the theorists and the chemists to actually make the whole thing function. And so I'll say something about basic kind of idea of magnetism realized by 3D electron systems and 4F electron systems. So sometimes that gets kind of forgotten in the course of talking about high-level kind of theoretical work, but these become very important to actually be able to understand the experimental kind of manifestations of the emergent phases. And then I'm going to throw in little bits about the particular techniques that we use. So this part I'll say something about what we call cold neutron spectroscopy, and there'll be quite a section here on neutron scattering. I think it's good for theorists that you know what actually goes on under the hood, and for some of you who are doing experiments, even though you may not be kind of focusing on scattering techniques, then I would like you to be aware that these tools are available, and actually by contacting and working with scientists at user facilities, you can bring that in as a component of your research. You don't have to be like, working with, if you want to, we can collaborate, but you can also just work yourself with these facilities. They're usually very, very excited about making contact to, the front end of interesting materials. So I'll say something about cold neutron spectroscopy, something about quantum information, quantum Fisher information, which is a new way that is being used to kind of classify some of these materials that is model independent, which is very important. And then at the end, I'd like to throw in something about ultra high resolution neutron scattering. Both some experiments we're doing in the time domain and some experiments we've been doing actually over some years using instruments that can go all the way to micro electron volt resolution. Sometimes people think of neutrons as being fairly coarse resolution, which sometimes it is, but you can actually go to really, really good energy resolution as well. And so I'd like to say a few words about that and how we use it. I'm starting off something I think fairly well known. Beautiful result from the 40s, actually. Lars Onsager, a Norwegian physicist and mathematician and chemist, who was able to actually solve this two-dimensional model of interacting spins. It really is a classical Ising model and a gigantic accomplishment in statistical physics. He could show that there is a phase transition at a specific temperature, known exactly, 2.27 times the exchange constant, and that's for ferromagnetic interactions between the spins on a triangular, on a square lattice. But if you change the interactions to be antiferromagnetic, nothing actually changes. It's kind of the same thing. You just have to do some transformations, and you have the same phase transition. So that's just a gorgeous result. And it changes completely when we add frustration. So when we add the possibility of returning walk, through the lattice that is an odd number of steps, then ferro and antiferromagnetism is totally different. I can still cover this lattice with I can satisfy all interactions if those are ferromagnetic interactions, and then there is a phase transition, and actually Barnier in 1950 calculated the critical temperature, but if you change it to antiferromagnetic interactions, then you just cannot make it all work out. And that's kind of the core of frustration, if you will, and recognized actually back in the 50s. Here's the ferromagnetic case, and this is just the energy as a function of temperature. And this singularity indicates the phase transition. Take a derivative, you'll find a nice spike. It's a different, critical temperature in terms of the exchange constant. But if you go to antiferromagnetic interactions, then actually there's no way to really get to that low energies, and you end up with an entropic state. So quite an amazing thing. So there's a finite entropy in the ground state, or in the low energy. The T equals to 0 phase actually has many different states that have the same energy, and so you have a certain entropy at low temperatures. So that is very exciting, because if we could then add quantum fluctuations, then we would expect to resolve this degeneracy, if you will, and that something else should come out which is not at all, you could say, kind of part of what you have just with the Ising interactions, but there have to be some other emergent phase that could result, and it's natural for us to want to understand what kind of state of matter is that. And of course, we're experimentalists, and so we have to find a physical material where we can realize this kind of thing. And you might initially say, well, how am I going to find an Ising spin? Because the spin is kind of detached from real space entirely. It just lives in its own kind of rotation in space. And the answer is basically spin-orbit coupling can couple the spin back into the real space. And you need to have the right conditions for that to actually come into play. Because if I have a low enough symmetry situation so that I end up with an orbital singlet state, and the filling is correct, then I may end up with a very isotropic spin degree of freedom. However, in the case of cobalt, with 6-fold coordination, cobalt 06, then actually, since there are 7 d electrons that can populate these now split, this is now split 5-fold. If I had isotropic conditions, it would be degenerate, but now it's split into a triplet and a doublet, and with 5 electrons to fill into this state, I end up with a triplet ground state orbitally, and then I'll have a spin 3/2 spin degree of freedom, but now because of spin-orbit interaction, then this degeneracy that otherwise would exist is now resolved or lifted into a spin 1/2, spin 3/2, spin 5/2. So it becomes a Kramer's doublet ground state, and it has all the character of a spin 1/2 degree of freedom, but when I flip the spin or rotate it, I'm actually doing stuff to the orbital sector as well. There's a spin-orbit coupling that is tied together the spin and orbital degrees of freedom, and therefore we can expect that the spin actually knows about what does the lattice look like, and so I can expect that I may be able to get a very anisotropic interaction coming in. But that's just the local physics, cobalt with its 6 ligands around it. Now I have to tie it into a lattice, and we want the triangular lattice, and that's something that is beyond certainly my capabilities as a person who works with solids, but of course chemists, this is really the realm, and Bob Carver is one of the experts in trying to figure out how to make interesting materials using these tools. And this is a compound that he introduced, I should say reintroduced, because many times there was a previous kind of chemistry that had discovered the compound, but then he was able to show that something interesting was going on as a result of the anisotropic interactions and the triangular lattice in this material. And he comes to us and says, what can you make out of this? And the wonderful thing is that everything seems to be built from this selenide polyanion. So this is SeO3, negatively charged, which has the 3-fold rotation symmetry built into it, and naturally can kind of link together these CO cobalt 6 units into a triangular lattice. So of course, this is just a gorgeous thing, and these are really high quality single crystalline samples that you can grow. The interaction is not a dipole interaction. This is very, very important to remember. It is a super exchange interaction. It has to do with d electrons which are hopping between these cobalt atoms, and they're passing through this polyanion site. But because those are now spin-orbital degrees of freedom, they have at least the possibility to be anisotropic, and it turns out that they do have a strong Ising component. There could also be a DM interaction, now that we have spin-orbit interactions, but because this selenide polyanion is so planar to it, it actually builds a structure that has a mirror plane, and that mirror plane really extinguishes the DM interaction. So I don't have that one, and so you end up with exactly the kind of Hamiltonian that we are interested in. It has the Ising term, it's Wannier considered, and then it also has a little bit of this transverse interaction, and that will throw in quantum fluctuations, which can lift the degeneracy of this Wannier manifold. And in our case, this one is 14 times larger than the transverse part. So it's not 100 times larger, which is good, because it's within our resolution. We can actually see the quantum fluctuations that result from this term. Okay, so you can calculate, you can try to calculate the interactions by tight binding or LDA plus U type calculations, which is getting better and better. In our case, we are just doing it phenomenologically. We do the measurements to determine what are the exchange constants for this Hamiltonian of this form, and we get a consistent picture. Okay, so now comes the little interlude of scattering to it. So this is we're going to take a look at this thing, and we're going to use neutrons to do that. But now let me say a few words about what we actually do with neutrons and why we like them. And I just wanted to say that you can find, of course, lots of information elsewhere. There's some wonderful books, and there's actually a set of online lectures which I planned and developed with other people from the field, and that's still available on this website, and you can kind of go through some of the details. It's like a graduate course we did over one semester. Okay, so The basic picture is it's a scattering experiment. So I have plane waves coming in, plane waves of neutrons coming in, and then I'm detecting the probability of transitioning in from Ki to Kf. And that depends on the wave vector transfer, which is vector subtraction of Ki minus Kf. So that vector is pointing in this direction. And I like to show this little scattering triangle. And we use it all the time as we do our experiments. That's Ki, that's Kf, which I just moved back here. Here's Q. That angle we call the scattering angle 2 theta. And the reason for that is this little piece of geometry from which I obtain that the length of this wave vector transfer, the length of it is 2k sine theta. But we have control over it as a vector. On our instrument, we know exactly where Q is pointing, and we can orient a single crystal with respect to that Q. So we have access to full kind of three-dimensional wave vector space in this kind of technique. And we also have access to the frequency domain. And this happens really because of kind of a piece of numerics in the sense, the neutron, first of all, barely interacts with materials. I'll talk more about the interactions. But secondly, it also happens to have a mass so that the ratio, so that the relation between the kinetic energy and the wave vector has this form. So, as this form, but also this particular numerical value, 2 millielectronvolt angstrom squared. So that's, this number is close to unity, which means that when I have sort of de Broglie wavelengths on the scale of the Lattice parameter, then I'm also able to have to appreciate energy transferred from the neutron, kinetic energy from the neutron transferred to the sample. It's very easy for me to resolve that. For X-rays, it's quite different because I'm coming in with kilo electron volts. And so if I certainly can have transfers, but I need like I need a really, really high resolution monochromator to be able to resolve things. And there's probably no way that I could get to like micro electron volt resolution. But for neutrons, this is quite possible for us. And so we have a very, very kind of broad dynamic range of energy resolution that I think is pretty much unique to neutron scattering. At the same time, we have spatial, access to the spatial information. This is now what the scattering triangle looks like. It got a little skewed because I transferred some of the energy from the incident beam to the sample, and that's now all I have left in terms of my wave vector. So now from the cosine relation, I get this relation between wave vector transfer and scattering angle, etc. And one of the things you notice is that now I cannot avoid to transfer some momentum to the sample because Ki and Kf do not have the same length, so they can never cancel each other out. So that kind of gives some limits in my phase space that I can access. So they've got a higher energy transfer relative to the kinetic energy of the neutron. I'm going to open up a wedge of phase space that I just can't see using this technique until I change the energy of the neutron. I could come in with a higher energy than I can, to some extent, encroach on that area. So this is just a little detail that becomes important experimentally. Okay, so that's the kinematics of it. But actually what's very interesting is that we can really, really calculate the scattering cross-section. So we have complete, I would say, very good understanding of what's actually going on there. And so let me just say a few words about that. So just to define the thing that we're measuring. And we're measuring what we call the scattering cross-section really in absolute units. And we can therefore make really kind of direct comparison to experimental predictions, even down to the prefactor. So just to define things, there's the flux is just the rate of neutrons passing through a cross-section. And I just want to mention that this is a really small number, 10 to the 6th, 10 to the 9th. This is about as many photons as would come from a candle. So we're kind of sitting there, and we need to use every neutron as it comes off. It's a very costly exercise to generate the neutrons. They bring a lot of information, but there's really not a lot of them. So we're always at the edge of resolution. We adjust things so we can see what we're looking for, but you will often see that there are some error bars because we pushed it to some kind of a limit. Okay, so this is the overall scattering cross-section, just the rate of neutrons scattered at all. So that just has it has the dimension of a cross-section. If you look at the dimensions, you can see that works. And for an atom, the cross-section is about a barn, 10 to the minus 24 centimeters squared, which is, in a very rough sense, the surface area of the nucleus. That determines how much nucleus can scatter very roughly. And then, but of course, that gives us kind of rather limited information. So we are interested in what is the distribution of scattering into different solid angles. So I'd like to see the angular distribution of scattering. And so I define this differential cross-section. So the rate of scattering into a certain solid angle, d sigma, that takes this form. And I can also resolve the energy of the final state. And that becomes this partial differential cross-section, which has these units of barn per steradian per millielectron volts. And that's the thing, essentially, that we're measuring in the end, and we can do it in absolute units. Okay, so what are the interactions? The interactions are the strong nuclear force that allows the neutron to interact with the nucleus, but it's just a brief visitor, so it sort of typically just passes through and does have this, the S-wave scattering from the nucleus. For some nuclei, the neutron is actually absorbed by the nucleus, and that's unfortunate. Then we don't see it coming off again. So then we may have to go to a different isotope. So it is fundamentally a nuclear interaction that we have between the neutron and the sample. It doesn't see the electron charge density at all. It is a neutral particle. However, there's a dipole-dipole interaction, because the neutron has a dipole moment 1,000 times less than the electron's dipole moment, but that gives us sensitivity to the spatially varying internal magnetic field in the material and allows us to couple to the electron, even though we have no charge. Through the dipole-dipole interaction, we do actually couple to the spin of the electron. So we know exactly what the interactions look like. A little later in the talk, I will emphasize the beneficial aspect of this nuclear interaction as compared to X-rays. With X-rays, it's just the charge density that determines the strength of the Thomson scattering. But for neutrons, it actually varies kind of by isotope and by element. And so we can be very sensitive to hydrogen inside a material that has lead in it. So with X-rays, we would just see the lead. But with neutrons, we see both the hydrogen and the lead. And so that very often there's actually some benefits in the structural determination with neutrons when we have light elements in the presence of heavy elements. Okay, now this is a little bit too much on one slide, probably in terms of formulae, but I just wanted, it's mostly just to emphasize that we really know what the scattering cross-section looks like. We work with this like on a daily basis at the instrument and writing our papers. This is just talking about magnetic neutron diffraction. And basically, we're then learning about the magnetic structure through this, what we call the vector structure factor. So just like with X-rays, we have the structure factor, summing over the sites with the space factor. With neutrons and magnetic scattering, it's actually a vector entity. So we learn something about the orientation of the spins through the structure factor, actually through this particular combination with wave vector transfer. And I'm going to use that in part of the talk at some point. But otherwise, the diffraction cross-section looks a lot like with X-rays. There's a delta function, which is enforcing that I can only transfer reciprocal lattice vectors of momentum to the sample. So I'm going to find the Bragg diffraction when I have a periodic magnetic structure at wave vectors, which would be the magnetic reciprocal lattice wave vectors. If I double the unit cell, I'm going to find new Bragg peaks appearing between the nuclear Bragg peaks, which are entirely due to the magnetic dipole-dipole interaction. So then for the inelastic scattering, everything can be formulated in terms of this dynamic two-point correlation function. And many of the theorists in the audience are very familiar with this kind of thing, or they may call it the Green's function. And we can directly relate what we measure to the imaginary part of the dissipated part of the generalized susceptibility of the system. And this is, again, and we have with absolute units, we can, in a sense, think of neutron scattering as a very, very advanced magnetization measurement, where we have both wave vector and we have energy in there. So it's like an AC, but also spatial, sensitive to spatial modulation as well. So that's what we're essentially measuring. Now, where do we get the neutrons from? They could come from fission or from what we call spallation. This requires a nuclear reactor. This requires a proton accelerator. So we're not going to have it at the university, but we have various of these facilities. Fission also generates 180 mega electron volt per neutron, which is why we have nuclear energy and facilities generating electrical energy through this process. But we're not interested in mega electron volt, so we actually have to slow down the neutrons by a moderation process. before we can make use of them. With spallation, there's actually less thermal energy generated, which is a good thing, because we're not interested in that for our purposes. And it actually just creates technical challenges to have all of this energy that we have to dispense with. So there are some significant advantages in using the spallation technique, basically hitting a heavy nucleus with protons and then splitting apart and generating, among many other things, free neutrons that can then be brought to the sample, or that then some of them will come to the sample, if you will. This is a chart of neutron flux versus time. This is kind of, you see Chadwick's discovery of the neutron back in the 30s. And then you see nuclear reactors coming to kind of a plateau. So around 10 to the 15 neutrons per square centimeter per second. And it really seems quite difficult to go much beyond that. But with spallation sources, we're able to go beyond that in terms of the peak brightness that can be created through the spallation. The pulsed nature of the spallation source is very important for that. Okay, so then in terms of the neutron detection, that all has to do with destroying the neutron, which is actually unfortunate, but we don't really have a way around that for now. So typically we'll use a material that absorbs neutrons, and almost entirely we're using helium-3 as a gas. We use a linear proportional counter, creating a proton and tritium in the process, and then detecting the charge shower that comes from that. This is what the detector looks like. There's an anode, cathode, neutron comes in, creates a proton and a tritium ion, and those get converted into by amplification through the gas itself, ionization of this gas. Then there's a charge pulse arriving at the anode, which is amplified and creates this type of spectrum. And this tail has to do with the protons that escape in the process, and this part has to do with the tritium that escapes in the process. But this is then how we detect the neutrons, and we detect them one at a time. So as they arrive, there's a pulse that we see in our charge amplifier. That was a neutron that arrived at the detector. Maybe a neutron that created a spin wave, or one that's scattered from the magnetic structure. But we really detect them one at a time, and that becomes important a little later in the talk. This is what the facilities, where they are and what they look like. This is at Oak Ridge National Lab. There's the reactor facility, and there's the spallation source that's now being upgraded. In about 10 years, there'll be a second target station here, even higher resolution and brightness. This is the NIST Center for Neutron Research. That's very close to where I live, which is Baltimore, Washington, Baltimore. Here's the reactor. And that's also partly why I live there, because I can access the reactor. It's really quite convenient. We built an instrument there. I'm going to show you some data from this instrument. But for the cobalt compound that we're going to start talking about, we used instrumentation at the Oak Ridge National Lab. And this is like a hugely complicated thing. We won't go into details about it. But fundamentally, you can be assured that what's happening is essentially the scattering triangle. Here's the incident vector, here's the scattered vector, and I'm keeping track of energy and momentum transfer. And you're going to see the scattering cross-section in absolute units as a function of wave vector and energy transfer. And this is what the sample tends to look like. We tend to have to mount many samples together to get enough intensity. I told you we're always kind of at the limit. And we use the fact that neutrons barely interact with material, and so I can use some aluminum, and that's perfectly fine. The neutrons just pass through it. I will see some signal from phonons and from Bragg diffraction, etc., but I can manage to subtract that out or handle it in some way, because my phase space for scattering is large. It's four-dimensional. I've got Q and energy, and this will just live somewhere else in phase space. That's fine. I would like to minimize it, but I can use this kind of methodology. Put it on a cryostat. Maybe put it inside a electromagnet, and we are off to the races. But first, we need to know something about the material, and this we do by regular kind of thermodynamic measurements. And here I'm showing you just susceptibility versus temperature for this triangular lattice Ising system. Actually, by looking at the inverse susceptibility versus temperature, we can get a measure of what is the strength of the interactions in the system from the Weiss temperature, and that will allow me to choose which instrument I should use. We've got many different instruments. I choose the one that's good for this energy scale, essentially. So here's magnetization measurements as a function of field. And that's the first kind of surprise that came in this material, is that we don't come up to the full magnetization, which is a little bit more than 3 Bohr magnetons. We just get to this level. So this is kind of surprising that we don't get so much magnetization there. But that was just because there was another shoe that had to drop. We had to go to higher fields, all the way up to more than 20 Tesla, and we used actually a pulsed high field facility to come up to this other level of magnetization. This is what we call a magnetization plateau, and that's very much part of the physics of this system. Now, if you look at dMdB, so the differential susceptibility, and that's actually what you measure in the more directly in the experiment, then you see that this transition actually has 2 little spikes to it. That was fantastic to see, actually. And we'll get back to that in a little bit, because we think that what's between these 2 spikes is a super solid state that has both density modulation as well as a superfluid component in there. And we'll get around to how that becomes connected to a spin system. So that's actually here. So this is the original Hamiltonian that we used to describe the system, but you can map it into a system of hardcore bosons with repulsive interactions by this little device here. So you basically relate a red spin or an up spin to the presence of a boson and a down spin to the absence of a boson. And then that will allow you to have the SC operator just becomes the number operating minus a half, and then this works. And then to have the commutation relations work out, this has to be the raising and the lowering operators. And then there's just a direct rewrite of the Hamiltonian, where the Ising term becomes this repulsion term between bosons, and the transverse quantum fluctuating term becomes a hopping term of bosons. When I flip an up-down spin to down-up, that's as if I move the boson from one side to the other. So the superfluid component will be related to the appearance of a finite expectation value for this kind of off-diagonal component. And so we're going to use that, and it's good to have in mind as we begin to look at the data. Okay, do you have any questions so far? Not yet, so please feel free to interrupt as we go along. And since I have another lecture, if we don't get to the end, we'll slide a little bit into the next lecture. So now I'm going to start looking at the magnetic diffraction from this material. And this was actually a surprise to us as we did the experiment. What I'm showing you here is the wave vector dependence. This is the triangular reciprocal lattice plane, and I'm showing you the intensity of scattering on this kind of false color scale, and I'm showing you actually data both at 0 Tesla and at finite field. And let me just go back once more to this I forgot to say that the Zeeman term maps onto a chemical potential for the bosons. For the bosons, yeah. And so I can actually vary the chemical potential by just changing my magnetic field. That's a wonderful variable to have as an experimentalist. You just have a dial to just adjust it. And so this is really gorgeous. And so I'm going to be able to change the density of bosons on the lattice just by changing the magnetic field. So this is in 0 field, so that would be 0 chemical potential. And this is when I put a big field on and I get into this 1/3 magnetization plateau. And this is what the diffraction looks like. I've subtracted off the high temperature diffraction from all the sample hold and all these other things. So all that's left is the magnetic component of scattering. And you see these 6 little dots showing up there. That was a surprise to us because we were told that this was an entropic state, but actually there's pretty much a long-range ordering that has occurred in the material. And these, just by their location, that's a √3 by √3 unit cell, which has 3 cobalt sites per unit cell. And so it's actually developed some kind of a long-range correlation in it. Now I can also look at the wave vector dependence in the perpendicular direction. So coming out of the plane, I also have access to that. And I'm showing that here, actually. And so this yellow line shows that there's actually very little wave vector dependence in the perpendicular direction. That's as we expect if there are no interactions between the planes, because then there's no correlations between planes, which means that there's no wave vector dependence in that for the scattering cross-section in that direction. So we see that directly. It's a two-dimensional spin system. It has fairly long-range magnetic order of the √3 by √3 variety. And so we can develop a picture for the spin structure, which actually looks something like this. It's not a unique picture, but it does describe the data. And so the interesting thing is that the moment per site is heavily reduced from the full magnetization. And also, I found it very interesting, and still do, that there's really no peak in the middle there. The peak in the middle would correspond to a uniform magnetization on the triangle lattice plane. But that one is completely suppressed. And this is, for me, was a bit surprising, because if I take 3 spins, and I'm going to have, Ising-like variables, they can be up or down. I can really just do 2 up and 1 down. There'll always be some magnetization kind of left behind. But what we're finding is that even though I develop long-range correlations, I'm completely able to avoid any regions that have, finite magnetization. Those are really extinguished from the structure. And so that means that if I have, I think I'm showing you, if this is like a down spin, then these 2 red sides need to be have half of the projection along the z-axis of a moment. So this is like a full moment pointing down, and then these will be 2 half moments pointing up, and they're actually canceling out the z-axis component. This in-plane component is something that we infer from the spectroscopy. I'm going to get back to that. It's very important for the identification of the nature of this low temperature state. Okay, so what happens when I come to a field? So I put 7 Tesla on. Now I get the little dot in the middle. And so that means that I have magnetized the system, as we expect. And interestingly, I still have lines of scattering along these outer peaks still are rods of scattering. But the peak in the middle, which we call the ferromagnetic peak, that one is a proper and full Bragg peak. It just dots. And so that is because I have magnetized the whole crystalline structure as a periodic crystalline unit. And so it becomes a full-out Bragg peak. But it doesn't imply that the antiferromagnetic ordering is correlated between planes. Those are still uncorrelated. So that is a test to the extremely two-dimensional nature of the system. Even at 0.1 Kelvin, it still is uncorrelated between the planes. Okay, all right. So that actually allows me to draw this kind of structure at 7 Tesla. There we get up to 3.9 UV per cobalt. And basically I have like minority and majority spins. Each blue spin is surrounded by 6 up spins. And then each red spin, I think, is surrounded actually by, it has as many up as down spins surrounding it. So that's the nature of the plateau phase, very stable. All right, so because the moment is heavily reduced relative to the full saturation, it means that there must be some quantum fluctuations. And so we're going to look for those using the inelastic scattering technique. That's a natural way to do that. And this is what it looks like. So this is 0 field and very low temperatures. And I'm just, the machine is counting the neutrons as they come off. And this is my wave vector axis. The various indexes for wave vector transfer in the brilliance zone of the triangular lattice. And this is energy transfer. And the color scale gives me how much intensity. And there's a lot of intensity in kind of bands. Here's one band, another band, and another band. And there's actually another band up here. These kind of equidistant bands. And we were not really expecting that. We probably should have, but now we understand kind of why this is a very, very natural thing to have in an Ising system. Because if you think of it, if I totally turn off the transverse part of the interaction, so I just have the ZZ term, then the excitation that I'm doing is just flipping a spin in its exchange field. And its exchange field is set up by the 6 spins that surround it. And if I have as many up as down spins, then the exchange field is actually 0. And it costs me no energy to flip this spin. That was my target spin to flip. And so that accounts for this low energy kind of sector. But then, because it is a quantum fluctuating spin system, I should also expect that there will be some spins which are surrounded by a preponderance of red sides and fewer blue sides. And so that actually will cost an energy to flip that spin. And it will cost exactly, if you get rid of, you have to worry about the delta S is 1 because it is a spin half degree of freedom, and so on. Then you'll find that this actually just gives me an excitation exactly at Jz. That's what we should expect it. So I can just read off my Z component of the exchange is going to be somewhere around 3 millielectron volts. And then, of course, I could also, in the course of fluctuating through the Barnier manifold, I could also have this kind of configuration, and that will cost me 2 Jz, and I actually see a bit of intensity up there as well. So that directly shows you that this is actually a quantum fluctuating state. Spins are flipping in different environments. It's a little kind of rough way of looking at it, but I think we're pulling out the right feature. Now, of course, this is an approximation because we do have the transverse term, and so the spin flip is not really just flipping a single spin. There are some correlations involved, and these go beyond the atom, because if I look at the intensity of this mode, you can see that there's actually some structure in reciprocal space. It sort of lives along the some boundaries. So that means that I'm not just flipping one spin, I'm actually doing some kind of a rearrangement of the structure that reflects this wave vector dependence. All right. So then I'm going to look individually at each of these regions, and I'm going to start off with the low energy part. Actually, this is the one that I'll focus on. And I'm zooming in. I'll change my configuration, and I come to actually a different instrument. This is another type of instrument. Yes?
I have a quick question on the last slide, actually. So should the flat bands of intensity, should it only go up to 3, and after that there should be no more?
Yes, right, yeah. That should be no more.
Cool.
So we have seen the upper one using terahertz spectroscope. Peter Armitage and his group has seen that. And we do have the data in the paper.
Would you get maybe even sub bands with nearest neighbors constantly? Or is it too far away?
That's an interesting point, but okay. That's a very interesting point. You would in general expect that. And we have another compound where that comes into play that's a more complicated situation. But what happens in this compound is that the next near and third near neighbor interactions are actually extremely weak and much weaker than the transverse term. So that means that the broadening of these bands, which is governed by the transverse terms, is beyond the contribution from the further neighbor interaction. So all of that is a lovely aspect of the system, actually. It really is focused on the transverse quantum fluctuation generating part, but not the complexity of the further range interactions. So, yeah. So then we go in and look at the really low energy part. And here, this was fairly coarse resolution. Actually, the data is, if you look with a different intensity scale, you can actually see stuff even with this resolution. But we go to a different instrument, also at Oak Ridge, called CNCS. And you get this kind of data in the low energy sector. And bear in mind, this is not kind of a spin wave excitation of some ordered state. This is fully generated by the transverse quantum fluctuating generating part in the presence, in this Barnier manifold. So with just Jz, I don't get any of this. But adding in the fluctuations actually lifts the degeneracy. And it favors a certain wave vector, which is the K wave vector, which is where we found those 6 points in the elastic scattering. So it makes sense that I have a fully kind of soft mode at that point. Actually, if you look in greater detail, you see that there's also a finite energy component. So there's both a gapless mode that comes all the way down, and then also a mode at finite energy. And we actually know where that one comes from. That has to be there also when there is a density modulation. But the presence of this gapless part of the spectrum, that is our indication of a broken continuous degree of freedom. So the Goldstone theorem, when you break a continuous degree of freedom, then there has to be a gapless mode. And so you ask yourself, where could that gapless mode come from? And I'm going to actually mention that a little later, because, but eventually we will relate it to this in-plane transverse component, because that's what can break the rotation symmetry. But I wanted to actually just look at the quality of these data by scanning. Just take a slice of the data at a fixed energy transfer. You just take this band, and you see this data here. This is symmetrized, I have to say, but the data is really outstanding quality. But it has been symmetrized in this projection. And you see these points. That's the gapless part. then you see these points which actually come from the M point, which also is kind of I consider it like a competing instability. You can see this is coming into view. If you look very carefully, then here at half of the K point, there's also a soft, like a lower energy mode there. That's not into view yet because I only showed the really low energy part. If I come up a little bit more, then you can just see these appearing, this kind of 6 spots here that comes from this part here. These have now become stronger because I'm passing through this minimum here. And then as you come even higher, this whole thing kind of comes together, and we have these kind of images almost looking like ARPA's data. And you can keep going, and then eventually you go beyond this kind of lower edge of the continuum, and you get into a region where you still have intensity. These are complicated features that are living at higher energy transfer, all the way up to 0.4 millielectron volt, which is way beyond the strength of the transverse interaction. It's about twice the strength of that, but you really have really a continuum of scattering with some accumulation of intensity along the low energy ridge. So this is something, it's really beyond any spin wave type theory, but it is very much in the realm of what can be done now with the IPEPs and DMRG type calculations, and many of you who do these kinds of things are probably aware of work that has been going on to try to describe these kinds of excitations. But it's just quite extraordinary that experimentally you have direct access to this, really complex many-body, quantum many-body phenomenon. Okay, so then I come back to this point of the gapless component, and what I want to say is that it can't be associated with the ZZ part of the correlation function because that's rotationally invariant, but it should be associated with the off-dying of the planar projection of the spin, and so that the presence of the gapless component indicates the presence of a transverse additional component in the order parameter. And then also these other features at the K half and the M point be associated with roton-like minima that indicate other competing instabilities that are not coming to fruition in this material, but perhaps with longer range interactions, one could actually pull this mode entirely down and get some other kind of an ordered state. So that's the basic story. Now, how am I doing for time? 2:20.
We have until 3, right? Yeah, we have until 3.
Okay, excellent. Okay, so I'll just keep my mind that. Good. So then, all right. So this is when we first saw this, we thought.
Sorry, 2:45.
2:45.
Yeah.
Okay. Yes, that's right. 75. Okay. So when we first saw this reminded us tremendously of spin half chains. So there's been a lot of work over many decades of this important model in condensed matter physics, including neutron work. And it's possible to see these continua of scattering that become associated with the 2 spin-on excitations. And so we were always interested in whether it's possible to kind of bind the spin-ons back together in some way. And that turns out to be really possible in this system. And so I really like these data a lot. So this is, I went to somewhat higher temperature, not intentionally, but the dilution bridge gave up. I decided to find something else to do with the time. That sometimes happens. And so we were sitting at 1.8 Kelvin. We thought, let's just go to higher field so it's not so problematic that we add higher temperature. And so then this is kind of the remnant of what I previously described, but with coarser resolution and at higher temperatures. But now I begin to apply field. And you can see kind of out of this morass, you get this lovely spin wave type mode that kind of appears. And so what's happened is that now I have a fully, I have introduced a gap in the spectrum, and I've converted the system from an entangled state into a product state that has single particle spin flip type excitation. So I really have magnon excitations now once I get into the plateau phase. And so this is the magnon, and actually here you can see the resolution. I mean, it's really tremendous resolution, very, very different from the continuum scattering that I showed you previously. It's not, because we don't have the resolution to see it, it's because it truly is broad scattering. But here we have a single particle excitation, and now we can use that to actually determine these the exchange constants. I won't spend very long emphasizing that, but it's really very important. I will say when we do our experiments, that we can both show like the dynamic correlations that are non-trivial and interesting, but also say what is the Hamiltonian that underlies all of that with some confidence. That's not always possible. Sometimes we actually don't know. We don't have a way of really measuring the Hamiltonian accurately, but in this case we do, because we have the plateau phase, and that should be quite well described by spin wave theory. And so we can do regular 1/s spin wave theory and calculate the scattering cross section, and we can get these exchange constants 2.98, consistent with what we saw from the rough analysis. But now we get the transverse part as well, which comes from the bandwidth of this excitation. So it's a direct kind of modeling. That's the calculator, and that's the measured. And it works pretty well. Okay, so I think I'm going to, I might skip a couple of slides. Or maybe this one I'm supposed to, this one I will show. So I'll show some data just to try to understand the overall phase diagram of this material as a function of field and temperature. And so this will bring us to specific heat and magnetization measurements. And this is the specific heat measurements at various fields. Now the very interesting thing is that when you go to zero field, that's when we do have these 6 little dots. And so we do have some fairly long range correlations, but there's no peak indicating a phase transition. These are all just kind of broad features in this specific heat. And that's not because of disorder or not good samples. Samples are excellent, but it's because this is actually not a proper second order, or it's not a second order phase transition. It's a 2-dimensional system which has a Kossler-Saulus type phase transition. And so these broad peaks are all that's left to indicate that there is actually a phase transition going on, but it's of the vortex and binding type. But then as we come up to higher fields, now there really is a sharp peak. And what's happened is that there we have a full permutation symmetry breaking, because the sublattices become the majority and minority sublattices, and that indicates like an Ising-like symmetry breaking. And so then I have a real peak in my specific heat, and actually that's a 3-stage Potts model once I have the field on, and that has a known critical exponent of 1/3, and this is our extracted critical exponent from these data, which is actually consistent with that. So we really understand structurally as well as thermodynamically what is this phase transition. It's a 3-stage Potts model. Then when we come to higher field, then we have to switch to magnetization measurements, because we didn't have access to specific heat at those very high fields. But this is what the data look like. I don't know where I have my, sorry, I don't know, I didn't show my field scale, but this is maybe 25 Tesla, and then we're coming down. And the thing I like about these data is you can see that the system really, really likes the 1/3 magnetization. If I don't give enough field, it'll just pull up by its bootstraps and get to that magnetization. If I get too much field, it actually pulls it back down to 1/3 magnetization. So that's a very stable, incompressible phase. And then up here, there's actually something interesting going on, which I'd shown you previously with that double peak in the differential susceptibility. And here I've assembled the same data as differential susceptibility versus temperature and field. And you can see, if you look carefully, that there are actually 2 maxima here. And that little sliver is this additional phase that we think is actually a super solid additional super solid state. That's a theoretical prediction, but these data are actually consistent with that. Okay, all right. So I think we've had enough of this, even though it's a nice thing. I'll just kind of summarize what we think we have here. So low fields, we have no sharp phase transition, but we have a quasi 2-dimensional order that we get into through a Kossler-Saulus transition. And there is evidence for U1 symmetry breaking through the gapless component of the excitation spectrum, and that's can be associated with the U1 symmetry breaking, which indicates the superfluid component, which in combination with the density modulation makes up a supersolid state. So I would say that the data is fully consistent with this theoretical prediction, but we still have more work, I think, experimentally to really see aspects of the static part of it. We haven't been able to see the in-plane component of the magnetization yet. That was what's on the other slide. that seems to be quite weak and difficult to see, but we're still looking. At intermediate fields, we have this one-third magnetization plateau from which we get the Hamiltonian, and we can see that it is really a three-state Potts model. And then at really high fields, we have this additional little sliver of a phase that maybe is second supersolid. That one is difficult to look at experimentally. 20 Tesla is quite hard, but we have plans to take a look for that as well. This work was all, there was a big collaboration with many people involved, and some of the main contributors are shown here. This is Bob Carver from your chemistry department, my long-term collaborator, Tom Chen, who is a postdoc in my group, and Ali Ghazimi, who has graduated, and he's now working with Blue Force. So if you buy a Blue Force dilution fridge, he'll come and install it. He may come and install it for you. Okay, any questions on this Ising triangular lens system? Yes?
So maybe I overheard. So you have some idea why these spin fluctuations are anisotropic? Why they show these anisotropic in your version?
The anisotropy. Which part of the?
I mean the fluctuations, they are not flat. They show anisotropy. You know, these couple of states.
You're thinking about.
Yeah.
This thing?
Mm-hmm.
This one? Oh, this stuff? Yeah, that I think basically, I mean, one way just like you could think of it is that that when I flip the spin, if I was to just flip the spin, this will be actually too costly. And so I'm making a transition into a correlated state that involves not just flipping this spin, but also rearranging this spin in some fashion. So it's really beyond what we can really express properly with the Ising model itself. It involves the presence of this transverse part of the correlations too. So basically, I mean, when I first saw this, my immediate kind of reaction, this is some kind of a singlet formation between pairs, because if I was to just lay out a lattice and form singlets between pairs in all different orientations, you would get exactly this kind of pattern, in fact. Because the singlet just produces lines of intensity like this along the zone boundary, and then the next singlet has the other orientation will produce the other set of lines, and finally they make up this picture. But this is not quite the right way of describing it. So I think we can say, however, that this is indicating an antiferromagnetic nature of the pair state that is retained as I make the excitation. But it's something that can be calculated with DMRG. Actually, they can look at this whole thing, and so it's often the case that we provide kind of the solution book. And so this is really. If it comes together with the Hamiltonian, then you should be able to calculate it.
Yes. Was a time of flight spectroscopy or digital axis?
This was all time of flight spectroscopy, and so I would say that we use both kinds of facilities, but all of the really high resolution stuff is that's done very, very well at the time of flight facilities. And I'll give another example of that. So it's pretty difficult to get. It's not impossible. IN5 at ILL has very good resolution as well. But this machine gets down to about 15 microelectron volt resolution. And we have another machine, or they have another machine that goes to 3 microelectron volt, which is, that's really spectacular. It's pretty difficult to do it. Not impossible, but you can't do it with this level of intensity, I would say. Yeah. Okay. All right. So then let's take a look at the next problem, which will be actually going to still the triangular lattice, but now go to Heisenberg spin. So a much more isotropic spin system. And this is, of course, the venue where Bill Anderson developed the idea of the resonating valence bond state as a possibly competing state with the ordered state on the triangular lattice at t equals to 0. So the paper didn't say this is what it is, but it's a beautiful paper. He said this is also a low energy state, which is a resonating valence bond state. And it really eventually, set off a search for materials that are fully dominated by this resonating valence bond state. But for a period, it was kind of disappointing because exact diagonalization showed that actually the long-range 120-degree order is what you get for near-neighbor antiferromagnetic interactions. But there were always materials that showed something different. There are both some titanates that I think are very interesting, but are difficult to grow as single crystals that show this absence of a phase transition to 120-degree structure. And also these organic magnetic materials in NMR showed, they show really no indication of a phase transition at all. And so there's been persistent sort of experimental indications that there is some kind of a strongly fluctuating state which is lurking around out there that needs to be properly understood. Maybe it could be accessed with competing interactions or anisotropic interactions, or maybe if you have charge mobility, charge hopping, if you're near the metal insulated transition. So these things were of interest for a long time experimentally, and I think it seems possible now more and more that we can access this kind of a spin liquid state, even though the material may have long range order, then the excitations actually probably should be described as spin excitations. But then there was a very interesting set of works that I think started off in 2015 with this lovely paper, where they put in second near neighbor interactions on the triangular lattice. So here's the triangular lattice. So second near neighbor is this interaction here. So this is the nearest, that's the second near neighbor. And so in this wonderful chart, this is a DMRG calculation by the creator of the DMRG technique, Steve White. And he's bearing, or they are bearing, the second near neighbor interaction from absent up to this value. And then by these arrows and these lines, they indicate different types of static order. And they actually show that in some range of the next near neighbor interaction, you can seem to completely get rid of the order. And that was an indication. They said that this was the discovery of a spin liquid state on the triangular lattice. And so other groups, some of them indicated here, have worked on this as well. It really is something that happens sort of between the 120-degree spin structure and the striped spin structure that's favored by the second near neighbor interaction. And then somewhere in between these kinds of ratios, then you get you have no long range order. It's some kind of a spin liquid state. And there's really serious theoretical work, numerical work that begins to identify which kind of spin liquid it might be. U1 Dirac spin liquid is a possibility, but also a Z2 gapped spin liquid may also be a possibility. I think there's still debates and studies going on. And of course, the interesting question is whether there will be an experimental system that can actually bring out this spin liquid in reality, so we can actually study it experimentally. Of course, experimentally, we always have disorder. That's just because of thermodynamics, so there's no way you can make a fully ordered structure with the solid state chemistry methods. And so I was interested to see this study from 2019 where they added in a disorder component with an amplitude delta to both J1 and J2, and then they have this kind of extended phase diagram where this is, this axis is what the other papers had studied, and this axis now introduces disorder. And one finds that actually it's a forgiving thing, that when you add disorder, you get a spin liquid-like state. Many of the characteristics are quite similar, but as you get to higher and higher disorder, it changes to something quite different. There's no fluctuations are kind of left. But so this actually may be helpful in a sense to identify materials, but also a challenge because we need to understand how much of the absence of disorder is due to the correlated physics and how much is due to disorder itself. And this is quite a difficult thing that I'm sure we're going to be working with for quite a while. Now, the model systems in this case turn out to be rare earth based. And so I just want to remind about the different kind of character of magnetism in insulating materials. And so just ordered by the shell which is generating magnetism. 3D was what we were talking about, but we were talking about a very special case where there was an orbital degree of freedom left and spin-orbit coupling, and became very anisotropic. But in many cases, if you think about copper, for example, or nickel in many cases, it can be fairly isotropic, and so it's really dominated by the intra-electronic repulsion and crystal electric field effects. When you come to 4F electrons, then you have the intra-electronic repulsion spin-orbit interaction is very strong, generating a spin-orbital degree of freedom, and then crystal field excitations will eventually lift that degeneracy, and you get these crystal field excitations. And in some cases, you can have a ground state, and that's specifically for rare earth ions that have an odd number of electrons, which are Kramer's doublets. And they can behave, they don't have to, but they can behave pretty much as a spin half degree of freedom. And that's the kind of spin degree of freedom that turns out to be possible to realize on triangular lattice with next neighbor interactions in a set of compounds called de la Fossites. So we're going to go to this part of our diagram. And in this part of the diagram, it's really important to understand the nature of your low energy multiplet. And so you actually need to know what are the effects of this crystal field interaction. And I just wanted to remind or indicate to people that neutron scattering is really a wonderful technique to figure out what is the nature of the low-lying multiplet. And there's a very, very easy experiment. So the powder sample, you throw it on the machine. In a couple of hours, you'll have the spectrum. And these lines here are excitations that they maintain the spin orbital quantum number, but the way that spin and orbital degrees of freedom are entangled is different in each of these levels. And the neutron can make transitions between those levels. Here we just use different incident neutron kinetic energies, 40, 80, and 150. And it's the same material and the same spectrum, but we're able to see more of the spectrum. And it was important to go all the way to 150 to get the highest energy excitation, up to 120 millielectron volts. And you could say, well, why are you doing this high energy stuff if you're interested in the low energy collective physics? It's because I need to know what the ground state multiplet looks like. And that requires really looking at all of these levels. And so now you do some fitting of the spectra as well as magnetization measurements, both so stability and saturation magnetization. Those you actually need to combine these things to get a reliable result. We've been burned once, and we're trying not to be burned again. But by combining those, you can then really get the whole kind of composition of the ground state Kramer's doublet. In this case, it was a neodymium ion. All right, now the materials that people have been looking at are these opasolite systems, and so here's one of them. Sorry, delaphosite type structures, and so it has this kind of crystal structure. This is the rare earth ion, and this is the 6-fold coordinated by selenium, and potassium is part of keeping these things apart. And you can change the alkaline site, and as you change it, it seems that you're changing the ratio between J2 and J1. So the thing that Steve White did to scan with his DMRG across this system, that corresponds to adding in different alkali elements to the system. And this is a beautiful set of work that I was not at all involved in, but this group of people did it. I think it's been quite influential. And it's published in this paper. There are other papers on the archive. And they've been able to measure, like we did for this Ising system, but now in a different energy range and for rare earth ions. They're using the same instruments, by the way. But here's the potassium terbium diselenide. This thing does have a magnetic order eventually, but it has no spin wave excitations. And the magnetic order is something that influences things at really low energies. But all of this other part of the excitation spectrum is really the characteristic excitations of this J1, J2 quantum spin liquid. And so they've been looking with Schwinger boson theory and DMRG to try to calculate that and have a pretty good agreement between the experiment and some of the theory. And this is where I was going to say a few words about this feature of quantum Fisher information as a way of characterizing these systems. But I think I'm getting sort of to the end of my time, so I think I'll just leave that. If you want to hear more about it, you can ask, or we can say something about it tomorrow. And I'll just end up by inviting your questions. And oh, I thought I had another slide. I think I have. Oh, here we are. I maybe have another slide. No, I don't. Okay, sorry about that. I thought I had to find it. I was gonna. Oh, here we are. Summary. This is my summary. My summary is that insulating transitional and rare earth-based materials can just a wonderful laboratory to study quantum many-body physics. And neutron scattering is one of the many tools and probes that we have to understand these systems. It gives access to a very broad range of energies and with spatial resolution on the atomic scale. And tomorrow we're going to talk more about, I think I might say a few more words about the insulating materials, but then I'm going to transition to exploring the interplay between magnetism and topological and metallic systems, and we'll be using neutrons to look at that as well. Thank you for your attention.
We have time for any questions?
Thank you so much for your talk. I have a question about rare earth materials. How difficult would it be to find the grounded state duplex characteristics for erbium oxide?
Erbium oxide, just ER203?
Yeah, E203. ER203.
ER203. That should be perfectly fine. We just need so that one. I think that has quite a few levels in it, so you need fairly good accuracy and good quality data to do it. But I think it should be.
Is it easy to work with erbium oxide? I don't know. I was told by experimentalists that it's not easy to work with erbium oxide crystal or something.
I mean, from a neutron perspective, it's fine. There's no problem. Dispersion is a problem, but it's a problem because it absorbs neutrons. But I don't think erbium has much of an absorption. And even if it does, we just go to another isotope if we can afford it, and then we can keep going. So I think that should be perfect. I think erbium oxide should be fine, and one just needs about 1 gram of power cell.
Thank you so much.
One question is, can the neutron scarings distinguish excitations on the edge compared to the bulk?
That's a very good question. And that is something we're very interested in, but it's fundamentally is a complicated thing because it really is a bulk probe, neutrons, and so I won't have enough spins that are kind of living at the edge unless I do something special. And we have actually been doing things and had access to edge states. And one of the examples we have is for the Haldane spin chain. So this is a valence bond solid state with a spin half degree at the ends. So what we did in that case to be able to probe the end states was we diluted, so replaced nickel by zinc or magnesium, and that created finite length spin chains. And by choosing the degree of doping, we could determine how long was the average chain length, and we could get enough chain ends that we could have intensity to be able to see it. And we were actually able to see the chain end states, but it's a little unsatisfactory in the sense that we don't have control over the chain lengths in that kind of scenario, so we have a random distribution. So what we're trying now, and we haven't been successful yet, but that's to make a thin film structure of spin 1 chains, and then you actually get a whole, like a monodispersed chain length. So it's on the way, and I think with the next target station at the spallation source, looking at thin film structures where you can have like a high fraction of your spins are at the surface, that now becomes a possibility. Yeah.
Yes.
Any more questions? All right, let's thank Professor Broholm once more.